the last topic that I want to talk about in reference to linear functions is about linear inequalities and systems of linear inequalities. Once we finish this, the remaining sections in chapter 1 are about limits and derivatives, just a brief introduction to those things so that we can practice them as we go through and review some more kinds of functions in chapters 2 and 3. But anyway, so let's talk about inequalities a little bit. Inequalities work the same way as equations, except with one additional rule, and that is that if we multiply or divide through by a negative number, then the direction of the inequality has to change. And to see why, notice that 3 is greater than 2. That's a true statement, right? 3 is greater than 2. But negative 3 is not greater than negative 2. In fact, negative 3 is less than negative 2, right? So if you take this statement and you divide through by negative 1, then in order to keep the statement true, the direction of the inequality has to switch, right? So let's practice. We'll find the solution sets. We'll write the solution sets in interval notation, okay? So solving this one, I would add 2, then divide by 3. So there's my solution set, okay? It's all real numbers less than 3. So negative infinity to positive 3. If you needed to graph it in order to get the interval, you could do that, right? It looks like that. So the interval is negative infinity to 3. Okay, see if you can do part B. All right, here's my solution. I'm going to move the 5x over, move the 2 over, divide by negative 2. Now when I divide by negative 2, this inequality has to change direction, right? So I get x greater than 1. So there's the solution in interval notation. Okay, so that's how inequalities work. No big deal. Sometimes we're dealing with more than one equality at a time, and those are called compound inequalities. Compound inequalities are a pair of inequalities joined by either the word and or the word or, as we've discussed in the past, means union, and, as we've discussed in the past, means intersection. Some and compound inequalities can be written as a single string of inequalities. For example, if you have this statement, x between 1 and 7, x is between 1 and 7, you could rewrite that as an and inequality. This means that x is greater than 1 and that x is less than or equal to 7. And by the way, here I read this statement, x is greater than 1. I was reading it from right to left, x greater than 1. If I read it from left to right, it would read 1 is less than x, okay? But anyway, so this and inequality could be rewritten as a single string of inequalities. It's not always possible to do that though. Anyway, let me just show you some examples. Let's find some solution sets to some compound inequalities. The way that we do this is we're going to find the individual solution sets, and then if we see an or, we're going to take the union of those two solution sets. If we see an and, then we'll take their intersection. Okay? So in this case, I'm going to have x less than or equal to 3. In this case, I'm going to have 2x greater than 12, so x greater than 6. So the individual solution sets are negative infinity to 3 and 6 to infinity. And since it's an or, I'm going to take the union of those two solution sets. Now in this case, they don't overlap at all, right? The first one looks like this. The second one looks like that. So there's no overlap between them. So there's no simplifying to be done. That's just it, right? That's our solution set. Let's look at another one. So x minus 3 greater than 0, or 2x plus 1 greater than, or less than or equal to 11. So Here I'm going to get x less than 3. Here I'm going to get 2x less than or equal to 10. So x is less than or equal to 5. So this one, the first one, the solution set is negative infinity to 3. For the second one, the solution set is negative infinity to 5. There's definitely quite a bit of overlap there. So of course I'm going to take the union of these two sets, but to see what the union is, it's maybe helpful to look at a picture, 3 and 5. The first one looks like that. The second one looks like that. So the union, remember, is the combination of the two sets. So the union is going to go, in this case, from negative infinity all the way up to 5. Okay. Aren't you glad we talked about unions and intersections earlier on in the course? I sure am, because now I don't have to take the time to explain why the union of these two things is this thing. Hopefully you remember that from the sections that we covered yesterday. Okay, moving on. Let's do some more. Let's do some and compound inequalities. So remember, ands are going to correspond to intersections. So let's solve. I'm going to add or subtract 3 and then divide by negative 2. And then here I'm just going to divide by 7. So for this inequality, the solution set x greater than 3, that would mean 3 to infinity. This solution set is x less than 2, that would mean negative infinity to 2. And I'm going to take the intersection of these two sets. So to see what the intersection is, a picture might be useful. I've got, or no, sorry, they should be open circles, right? That and that, I think, are my solution sets, my individual solution sets. And there's no overlap between them at all, so the solution set here is empty. In other words, there is no real number that will simultaneously satisfy these two conditions, right? You can't be both bigger than 3 and less than 2 at the same time. So, empty set. Part D is another and compound inequality in disguise. You could split this up the way that we looked at on the previous page, so that you have, the statement negative 13 is less than or equal to 3x plus 2, and 3x plus 2 is less than or equal to 8, and then solve like usual. But it's not even necessary to do that, because you can work with this the way it is. Just remember that whatever you do to the middle, you need to do to the outsides as well. So if I subtract 3, so if I want to subtract 2 to solve for x, I can do that as long as I do it everywhere, right? And then if I want to divide 3 by 3, once again, that's legal, as long as I do it everywhere. And then what's nice about this is that I don't have to worry about taking intersections or anything like that. This means exactly what it looks like. This means, well, x is bigger than or equal to negative 5, but also less than or equal to 2. In other words, x is between negative 5 and 2, just like it looks like. So the solution set would look like negative 5 to 2. And that's it for that. Okay? One thing that I'll warn you of with this type of problem is that students sometimes will do stuff like this. They'll say, I don't like that there are 2 inequalities, so I'm just going to get rid of this 8. And then they'll say, okay, so negative 13 minus 8 is negative 21. We have 3x minus 6, and then this rest of it, it just magically disappears. And that's wrong, okay? You're allowed to subtract through by negative 8 if you want, but 8 minus 8 is not nothing, it's 0, right? It's 0. So you would still have, you would still have this compound inequality that you have to deal with. And notice that you're not any closer to solving this than you were when you started. So this is legal, but it's just not useful. And I think the reason students do this oftentimes is because they think that 8 minus 8 just, well, it just disappears. So there's nothing here anymore. And that's not true. Okay, that's not true. So don't do that. Okay. So these inequalities that we've solved so far, they've all been one-dimensional, right? There was only one variable in them. But just like we had with linear equations, we could also have linear inequalities with more than one variable. And there would be infinitely many solutions to these kinds of inequalities. So for example, let's consider the inequality 2x plus y is less than or equal to 1. You could plug in like 0, 5. That would be, oh, that wouldn't be a solution. But 0, negative 5 would be, or negative 2, 0 would be, or negative 2, negative 7 would be a solution. Right? There are infinitely many solutions. What we want to do is describe the solution set. But describing the solution set algebraically is not very illuminating. Because the solution set to this, to describe it algebraically, you would just write, well, it's the set of all ordered pairs x, y, such that 2x plus y is less than or equal to 1, right? Like it's not very illuminating. So, so when we describe the solution sets to these, we like to do it graphically. So we're going to practice graphing solution sets to inequalities. In this case, since we have two variables, our graphs are going to be two-dimensional, graphed in the plane, instead of one-dimensional, so they're not going to be graphed on the number line like this. They're going to be graphed in the plane. To graph an inequality, like this one, we start off by graphing the boundary line. So you just replace the inequality with an equal sign and then graph that. That's the boundary line. And then we shade in the region where the inequality is true. When you graph the boundary line, use a dotted line if the inequality is strict. Use a solid line if the inequality is inclusive. And then to decide where to shade, we usually use a test point. So we pick a test point that's not on the boundary and we plug it into the inequality. If the resulting statement is true, then we shade on the side of the boundary where the test point is. If the statement is false, then we shade on the other side of the boundary. So let me walk you through a couple examples. So let's do this one, 2x plus y is less than or equal to 1. I'm going to start off by graphing 2x plus y equals 1. And since this inequality is inclusive, I'm going to graph this boundary line with a solid line. Okay, I think the easiest way to graph this one would probably be to put it in y equals mx plus b form, right? By just moving the 2x over to the other side. So my y-intercept is 1, and my slope is negative 2. Down 2 over 1. So it's going to look like this. Okay, so there's our boundary line. Now, to see which side of the line to shade on, we plug in a test point. And it can be any test point you like as long as it's not on the line. So for example, the point 0, 0 is not on the line, so I can use 0, 0 as my test point. So my test point, 0, 0. If I plug that into the inequality, I get 2 times 0 plus 0 is less than or equal to 1. I want to know if that's true. Well, 2 times 0 is 0, and 0 plus 0 is 0. 0 is less than or equal to 1. That's true. So since I got a true statement when I plugged in this test point, that tells me I'm going to shade on this side of the line where the test point was. Okay, and that's that, right? That's what that inequality, that's what the graph of that inequality would look like. So what this means is that any point that you pick on this side of the line is going to be a solution to the system. For example, negative 4, 1, 2, 3, 4, 3. Negative 4, 3. That point right there. It should be a solution to the system. Let's see. If we plug in negative 4, we get negative 8. If we plug in 3, negative 8 plus 3 is negative 5. Negative 5 is less than or equal to 1, so sure enough, right, that's a solution to the system. Or it's a solution to the inequality. Whereas if you pick any point up here, it's not going to be a solution. Like if I plug in 4, 1. 2 times 4 is 8. 8 plus 1 is 9. 9 is not less than or equal to 1. So that's not a solution to the inequality. Okay, so that's why we do the shading here, because we're indicating where our solutions live, right? All of our solutions live they live below the line over here. Okay, let's do another one. X minus 3y is less than or equal to, or is strictly less than 0. So this time when I graph the boundary line, x minus 3y equals 0, I'm going to graph it with a dotted line, okay? Because the numbers that are on, or the ordered pairs that are on the boundary line, in this problem, they're solutions to the inequality. In this problem, they're not going to be, so I indicate that with a dotted line. Okay, same trick as before. Negative 3y equals negative x. So y equals 1/3 x. So my y-intercept is 0, and my slope is 1/3. So I'm going to go up 1 over 3. And I can do this in either direction, right? And then connect the dots with a dotted line. Okay. So there's my boundary. Now I need to figure out which side of the line to shade on. I can't use 0, 0 as my test point this time because 0, 0 is on the boundary. So I have to use something else, maybe, I don't know, 0, 1, this point right here. So my test point is 0, 1. If I plug in 0, 1, I get 0 minus 3 times 1 is less than 0. I want to know if that's a true statement. 0 minus negative 3 times 1 is negative 3. And that is a true statement. So I'm going to shade above the line this time, because that's where my test point was, and when I plugged in my test point, I got a true statement. And that's that. Okay, so that's how graphing inequalities works. You could have a system of inequalities, right? A system of linear inequalities like this. And again, describing the solution set to this system algebraically is not very illuminating. The solution set to this system would be the set of all ordered pairs such that 2x plus y is less than or equal to 1 and x minus 3y is less than 0. Not very illuminating. So again, to get a better understanding of the solution set, we're going to graph the system. These are the same as what we graphed on the previous page, I believe. Yeah, so I'm just going to cheat and use my work from before. Okay, so there's my first boundary. Oh man. Okay, there's my first boundary. I don't know why it was so hard for me to do that. There's my first boundary. Then my second boundary is this one. Gets a dotted line, right? Okay. Now the solution set to the system is going to be where the shaded areas overlap. So you could do this a couple ways. You could either shade both and just shade them in different directions so that it's really clear where the overlap is. Or you could try to reason out where the overlap is. Let me make sure the inequalities are going the right way. Less than or equal to, less than, less than or equal to, less than, yeah. So I already know that I'm going to be shading, for the first one, I'm going to be shading below the line. For the second one, I'm going to be shading above the line. So I'm going to be shading here and here. They're going to overlap right here in this upper left corner, okay? So you could just shade that in and only shade that part in, and that would be a good way to show your work. But the other way, like I said, would be to do both shadings, just do them in a different direction so that it's really clear where your overlap is. So I shade above the line, above the dotted line, and below the solid line. if I do that, I end up with something like this, and then it's really clear that this is where they're overlapping, right? So my solution set is all of this stuff, right? It's all of this stuff. Okay, that gets kind of ugly, I guess, but there you go. That's the solution set. Okay, so that's how graphing systems of inequalities works. Now, here I want to pause and remind you again to be careful with the notation. Okay, this thing right here is a system of equations. If you want to graph a system of equations, you just graph the lines, and the solution is the point where the lines intersect. There's no shading required here, right? No shading is required at all. This is a system of inequalities, like what we just saw. Here, you have to shade to indicate where your solutions live, above or below the lines, right? And the solution region is going to be the place where the individual solution sets overlap, right? But you have to do shading here. But you graph the entire line, graph the entire boundary lines, and then shade, and where they overlap, that's the solution region. This is a piecewise function. This is a completely different beast. It's completely different from these other two things. Don't shade. Just because there are some inequalities here, that doesn't mean you're going to shade. This is a piecewise function. What this function means is you're going to graph this part, you're going to graph this line on this portion of the domain, and you're going to graph this other line on this other portion of the domain. But you're not going to do any shading at all. Okay? So try to keep these things straight. Okay? They are different things. Okay, so with that note, now let me just mention a little bit about applications of these things. You might think, well, why do we care about like finding solution sets to systems of inequalities? Well, one of the types of application problems that comes up is when you're dealing with systems of inequalities has to do with optimization problems. So optimization problems require us to find the maximum or the minimum value of a function within a certain region, and we call that region the constraint. The constraints for these types of optimization problems are usually systems of inequalities. Okay. Now, in order to solve these problems, a couple pieces of information are going to be useful. So first of all, the intersection of two boundaries in a system of inequalities is called a corner point. And second of all, a point at which a function achieves a maximum or minimum is called an optimal solution. So now we have this following fact. If f is a linear function, then the optimal solution must occur at a corner point. Okay. So let's practice. Let's practice finding some optimal solutions. This one says, maximize the function f of xy equals 2x plus 3y subject to these constraints. Notice that your function here takes an ordered pair as the input, right? So that's kind of interesting. But let's see if we can maximize this function subject to these constraints. So I'm going to start off first of all by graphing the constraints. So graphing the top one, I'm going to use intercepts. If I plug in 0 for y, you get 3x equals 15, so x equals 5. If I plug in 0 for x, I get 5y equals 15, so y equals 3. So there's the first boundary line. The second boundary line is x equals 0. That's just going to be a vertical line through 0. Right, that's basically just the y-axis. And then the third boundary is y equals 0. That's a horizontal line through 0. That's basically just the x-axis. So we're interested in maximizing this function subject to these constraints. And to get an idea for where we're dealing with in the plane, we should do some shading, right? So 3x minus 5y is less than or equal to 15. That was this boundary line right here. I suspect that we're going to be shading below that line, okay, because it's a less than or equal to. So I think we would shade below the line. X greater than 0 would be shading to the right of the vertical line, and y greater than 0 would be shading above the y line. So where all of those things intersect, below this line, to the right of that line, and above that line, we're going to be shading inside of this triangle right here. Right? So these are the constraints. Right? So we want to maximize this function inside of this little region right here. Okay? And what the fact from the previous page tells us is that the optimal solutions are going to happen at corner points. Corner points are intersections of the boundaries. So this is a corner point, this is a corner point, and this is a corner point. So our three candidates for optimal solutions are the points 0, 3, 5, 0, and 0, 0. So to figure out which one of those, we want to maximize this function, right? So to figure out which one of these is the maximum, we just have to plug them into the function to see. So if I plug in, well, I'll start with 0, 0. If I plug in 0, 0, I get 2 times 0 plus 3 times 0, which is 0. If I plug in 0, 3, then that means to plug in 0 for x and plug in 3 for y. That gives me 9. If I plug in 5, 0, that means I'm going to plug in 5 for x and 0 for y, and I get 10. There's my maximum value, right? So the largest that, notice that this function can get bigger and bigger and bigger. As long as x and y keep growing, this function is going to grow. But subject to these constraints, the biggest that the function is ever going to get is 10. Right? So inside of this region, the largest output value is going to be 10. That's the maximum. Okay, so we would say something like this. So the maximum value is 10, right? And this happens at 5, 0. So the maximum itself is 10, right? That would be the answer to the question. But if you were asked, when does the function achieve its maximum? You would say, well, it achieves its maximum at the point 5, 0. Okay? So that's that. If, note, on this same problem, if instead of maximize, the problem had said minimize, then we would say the minimum value is 0. And it happens at the point 0, 0. So if instead of maximum, the problem had said minimize, then we would say min is 0, and it happens at 0, 0, right? Okay. So let's do another example. Let's minimize this function, f of xy equals 4x minus 5y, subject to these constraints. Okay, so same deal. I'm going to start off by graphing the boundaries. 5x equals 35, so x is 7. 7y equals 35, so y equals 5. Okay, so there's my first boundary. For the second one, I think I'm not going to use intercepts. I think I'm just going to put it in y equals mx plus b form. So I would get 7y equals 2x. So y equals 2/7 x. So my y-intercept is 0. And my slope is 2/7, up 2 over 7. 6, 7. So there's my second constraint. And then the third constraint is easier. It's just a vertical line at x equals 0. And then as far as the shading is concerned, here I would be graphing, or I would be shading in below this line. So I'm shading below this line. Here I'm shading above, so I'm shading above that line. And here I'm shading to the right of the, so it must be this triangular region in here. So the possible maximum or minimum values are going to take place at corner points. Here's one. Here's another. 0, 5, 2, 3, 4, 5, 0, 5. And then here's another. And this corner point, I don't know. I'm going to have to find it. That corner point is going to be the place where these two boundaries intersect. So it's these two boundaries. So what I want to do is solve the corresponding system of equations, right? So I want to solve 5x plus 7y equals 35 and negative 2x plus 7y equals 0. Okay, so if I want to solve this system of equations, oh, this is already nice, right? I can just subtract the two equations. If I subtract these, just be careful with the negative signs, but I have 5 minus negative 2, that's 5 plus 2, so 7x. And I have 7y minus 7y, that's 0, so the y's cancel. And then 35 minus 0 is 35. Okay, so x equals 5. So 1, 2, 3, 4, 5. So 5. And then what does y equal? Well, I'll plug that back in, maybe to this top one. So I'll say negative 2 times 5 plus 7y equals 0. Negative 10 plus 7y equals 0. So 7y equals 10. Y equals 10 over 7. That's not very nice, right? 10 sevenths. 10 sevenths, let's see, is about 1.4, so it's about 1.4. That looks about right, the way that I graphed it. But anyway, 10 sevenths. Okay, so now that we know where the corner points are, we can see where our optimal solutions are. So to do that, we take turns plugging these into the function. So starting with 0, 0. Right, f of 0, 0, 0. If we plug in 0, 5, and we get negative 25. Okay, and then if we plug in 5, 10 sevenths. We get 20 minus 50 sevenths. Well, 20 sevenths would be 140 sevenths, I guess. 140 minus 50 is 90, yeah, so we get 90 sevenths. Yeah, that makes sense. 90 sevenths, which is like 12.9-ish. So this one is clearly our maximum value, and this one is clearly our minimum value. We were asked to minimize the function, so our answer is the minimum is negative 25. And it happens when x is 0 and y is 5. But there's the answer, right? Whew, all right. So, so that's how we do optimization problems. Now you may wonder, yeah, but what are optimization problems good for? Well, you're going to wish that you never asked. No, we'll look at this example. It's an interesting one. Optimization problems. So here's an example where an optimization problem could come in handy. says the Florida Juice Company makes two types of fruit punch, fruity and tangy, by blending orange juice and apple juice into a mixture. The fruit punch is sold in 5-gallon bottles. A bottle of fruity earns a profit of $3 and a bottle of tangy earns a profit of $2. A bottle of fruity requires 3 gallons of orange juice and 2 gallons of apple juice, while a bottle of tangy requires 4 gallons of orange juice and 1 gallon of apple juice. If 200 gallons of orange juice and 120 gallons of apple juice are available, find the maximum profit for the company. Maximum profit for the company. Go ahead and pause the video, reread it, make sure that you've got a good grasp of the information. Try to organize the information in some way that makes sense to you, okay? I'm going to go ahead and give you the solution though. So make sure you've paused the video and given it some thought before you watch, okay? At least I think I'm going to give you the solution. I haven't looked at this problem in a while, so I might not, I might struggle a little bit, but let's try it out. What I think is that since we want to maximize the profit, it might be a good idea to get a function for what the profit is, right? Well, we know that a bottle of fruity earns a $3 profit, and we know that a bottle of tangy earns a $2 profit. So for every bottle of fruity that I sell, I'm going to earn $3. For every bottle of tangy that I sell, I'm going to earn $2. So let's say that I sell X bottles of fruity and Y bottles of tangy. So let me write that down. So X equals number of fruity sold, and Y equals number of tangy sold. So then my profit function, f of xy, is going to be 3 times x, right? $3 for every bottle of fruity sold, 3 times x, plus 2 times y, $2 for every bottle of tangy sold. This is the function that I want to maximize. And I want to maximize it subject to certain constraints. What are those constraints? Well, the constraints are that I only have 200 gallons of orange juice available and I only have 120 gallons of apple juice available, right? Let's see. How much orange juice am I going to use? So maybe I'll say my constraints are down here, but how much orange juice am I going to use? If I produce X bottles of fruity, a bottle of fruity requires 3 gallons of orange juice. So for every bottle of fruity that I make, I need 3 gallons of OJ. So 3x gallons of OJ in total to produce the fruity variety. The tangy variety requires 4 gallons of orange juice. So for every bottle of tangy that I make, I'm going to need 4 gallons of orange juice. So the total amount of orange juice, that I'm going to use is 3x plus 4y. I need that to be less than or equal to 200. Okay, because only 200 gallons of orange juice are available to me. Total amount of apple juice. Well, for the fruity variety, I need 2 gallons of apple juice, and I'm going to make X bottles of the fruity variety. For the tangy variety, I just need 1 gallon of apple juice. So that's the total amount of apple juice that I am going to use, and I need this to be less than or equal to 120, because I only have 120 gallons of apple juice available to me. Okay, so these are my constraints. Those are the constraints that I'm working with. Okay, so let's work this out. First of all, let me get a graph. The graph doesn't have to be beautiful. I've already made it ugly. Let's get a graph though. So if I plug in 0 for x, then 4y needs to equal 200. 200 divided by 4 is what, 80? 50. Oh, holy schmoly. Yeah, 50. So y equals 50. If I plug in 0 for y, I get 3x has to equal 200. 200 divided by 3 is about 66.7. So there's my first graph. There's my first boundary. My second boundary, same deal. If I plug in 0 for x, y is 120. Oh, that's way up here. So 50, 100, maybe 120 is about there. If I plug in 0 for x, or sorry, 0 for y, I get 2x equals 120. So x would be 60. So there's my second boundary. And those are the only constraints. So, so the only place where this function is going to be maximized is right here where the functions, where the boundaries cross, right there at that corner point. So to figure out where the boundaries cross, I should solve this system of equations. So I should take 3x plus 4y equals 200, and I should take 2x plus y equals 120 and treat it like a system. I think I'm going to eliminate the y's by multiplying the bottom by -4. -480. I can add these up. And x equals 56. Okay, so this is the point 56. And then what's y? Well, I can plug it back in somewhere up here. I can say 3 times x plus 4 times y equals 200. 3 times 56 is 168. And I get 32 when I subtract the 168 over. Okay, so y equals 8. I can do that one in my head at least. So there's my corner point. It's 56.8. So now to maximize the profit, I'm going to say f of 56.8 equals 3 times 56 plus 2 times 8. And that comes out to 184. Okay, so there's my maximum profit. Okay, so there's my maximum profit. Now, how do I get that maximum profit? Well, I get that by producing 56 bottles of the fruity variety and 8 bottles of the tangy variety. And that makes sense, right? Because the fruity variety brings in a larger profit. So you want to produce as much of the fruity as you can. The problem is you can't just make only fruity, because if you make only fruity, you're going to have a bunch of orange juice left over that you could have used to make tangy, right? So there's a balancing act that you have to kind of perform, and this is how it's done. So you're going to make mostly fruity variety, but you're going to make some tangy variety as well in order to maximize your profit. In other words, if you only made fruity variety, if you only made the fruity variety, then you'd only be able to make 60 bottles of it, right? And your profit would have been 3 times 60 would be $180. So you wouldn't make quite as much. You'd only make $180 if you only made the fruity variety. That you can make this combination of fruity and tangy and use up all of your juice or most of your juice and make a little bit more. So that's the idea. In the real world, problems like this would be much more complicated. But this is the idea behind how they're solved. And so that's why we look at stuff like this. Okay. But that does it for our review of linear functions.